Hello. Good afternoon, everyone. Am I audible?
Yes, I am audible.
Yeah. I'm audible, right? Yeah. Okay, so if you have any questions, please type in your questions. I mean, I'll be happy to reply. Yeah, you can ask any question if you, Mr. Athar, have you got any question? Yeah, so Mr. Athar, I mean, there'll be no formulas which will be given. So if I'm audible, you can type yes, and then I'll answer. Otherwise, I'll type. So in the question paper, there'll be no formulas which will be given. So you have to basically remember the formulas. Yes. OK, so you'll have to remember the formulas because this is a course where uh, it is required to remember the formulas. OK. So we'll not be asking any proofs or something like this. But basic formulas you should know. Whatever was there in the assignments, basically. That much you should, if you remember any formula related to those, it should be fine. And there'll be many questions which will be conceptual. So rather than solving any problem, there'll be definitely some problems. There'll be some numericals that you have to solve, but there'll be a lot of problems. There'll be conceptual where you don't have to actually derive anything or something like this, but you have to remember basically. It always helps to correctly remember the formulas. So is it fine? Does that answer your question? OK. So how was the course? Tough, easy? Let me ask some questions then. Was the course helpful? OK. So yes, so you can also solve for exercises week 11 and 12. So that would be really helpful for your final exams.
Am I audible?
Yeah, Mr. Harsh Makwana and Mr. Ashish Devgare. I mean, you're on YouTube, I think. So good afternoon to you both. If you have any question, you can type basically in the chat box. I'll try to answer from here. Yeah, good afternoon, Mr. Praveen. If you have if you have any question, please type in your questions. Because on the sheet, I didn't receive any questions. On the Google Sheet, I don't have any questions. So if you can ask some question, that would be fine. It's not just any question. You can also give any suggestion that you have for this course. Maybe with that we can improve this course for the future students. That also, I mean, we can do in this interaction session. Okay. Okay. So, Mr. Harsh, uh, am I audible to you? You can type yes in the YouTube chat box and then if you type in the chat box, yes. Okay. So they can hear me on the YouTube, right? Okay. So, okay. So, Mr. Harsh, stretch is simply the uh, length, the final length divided by initial length. You can, or something like this. It's just the deformation that is stretch. Okay. Strain, on the other hand, takes into account both the, I mean, it may have takes into account both the deformation like stretch and rotation, both. Okay, so it may appear to be same. So for the case of 1D, these both quantities, strain and stretch, are basically the same. But for a general situation, strain is much more a general term than stretch. Okay, is it clear, Mr. Harsh? Yeah, Mr. Harsh, is it clear? So which one is more convenient to work practically, in the material configuration or in the spatial configuration? Yeah, so basically, okay. So basically, I think you want to ask whether you should use strain or stretch or something like this, right? So basically, from your lectures, you might remember that your equation of motion or equilibrium equation is written in the spatial configuration because that is the current configuration. Okay, so all your measures of strains or whatever are in the spatial configuration. Okay, so if you can be more clear about this, I'll be able to answer. Okay, so do you mean whether we should use strain in the material configuration and stretch in the spatial or otherwise? Is it your question? Is it the question that you wanted to ask, Mr. Harsh? Okay. So, yeah, Mr. Athar, first, let me answer Harsh Makwana's question. Okay, so application of this course in the nuclear field. I think you want to ask in the nuclear, nuclear energy and all this field, right? So basically, this course is like, uh, I mean, not entirely continuum mechanics and not entirely nonlinear FEM. It's like if you give, it gives you a taste of, or gives you a feeling how, given a particular material model, which in this course was hyperelastic material model, how do you actually go and uh, set up the equations to be solved on a computer? Okay. So in a nuclear field, most probably instead of an hyperelastic material, you may have some kind of hyperelastic material if you're using rubber or something like this, but you may have certain kind of metals, okay, and all those, uh, and you wanted to study how these metals and all behave under certain loading condition. So this course would be a stepping stone to understand more advanced formulation which are required in these fields. Okay. So once you have done this course, you have an idea about the building blocks of how to set up nonlinear finite element equations, how to linearize, what is meant by linearization, all these terms here you'll you'll again encounter when you do numerical simulations in the nuclear energy field. Okay, so what I can say is till kinetics, whatever was there, the basics of that will be used in any field, not only nuclear, any field. But after that, whatever we discussed, just the material model you have to change. Otherwise, the formulations and all will remain the same. I mean, you may have some external, new forces coming in. That's all. But you know how to do linearization, how to discretize, how to do linearization, all, and how to solve nonlinear equations. All this you know. So you might remember towards the end of the 12th week lectures, we had something on ductile fracture. So the application of these formulation in the ductile fracture was also shown. So you can apply this course in any field you want. Does this answer your question? Okay, let me take the question of Athar now. The push forward of the second Payala-Kirchhoff stress tensor to the current configuration gives the Kirchhoff stress tensor. Okay, let me just open. Yeah, this second Payala, right? You wanted to ask. Yes, so let me write somewhere. Yeah, so Athar, when we say that write true and false for this assertion, which means that I'm making a statement here that the push forward of the second Payala-Kirchhoff stress tensor, that is S, to the current configuration. Okay. So as you remember, the second Payala-Kirchhoff stress tensor resides in the material configuration. That is the initial configuration. Now, when you take that stress to the current configuration, that is the uh, spatial configuration, then the second Payala-Kirchhoff will transform itself to some other, stress tensor, which is there in the current defined in the current configuration. So what I'm saying is the push forward of the second Payala-Kirchhoff stress tensor to the current configuration. Okay, so when you take a second Payala-Kirchhoff S, capital S, from the material configuration to the current configuration, I'm saying it will be the Kirchhoff stress tensor. Now you have to answer whether this is correct or not. Okay, whether this is a true statement or it's a false statement. Okay, so you might remember that the push forward of, S. So this is carried out by, this will be carried out by pre-multiplying and post-multiplying the second Pala-Kirchhoff stress tensor with the deformation gradient tensor, F. Okay. So, it will be F S F transpose equal to J times of sigma. Now, what is J times sigma? So J times sigma is nothing but the Kirchhoff stress tensor. Okay. So if tau, that is J sigma, is F transpose, then to me it appears that the statement is true. Okay. So you just have to see the formula for the push forward of the second Pala-Kirchhoff stress tensor, and you have to see whether this statement is correct. Okay. Is it fine, Athar? Mr. Athar? Okay. So next question is from Mr. Ashish Deogre. Shall computer programming be part to be explored? Also, which software shall we use? Okay, that is Mr. Harsh question. Computer programming, yes, definitely this was not part of this course. So basically what we did was we set up the nonlinear equations. And then we just set up the Newton-Raphson method. We did not apply or write a computer code for that. Okay, but you might remember that in the Newton-Raphson method, we did solve a system of two equations, nonlinear equations. So the same system of nonlinear equations would come up in whatever we derive linearize in this course. Okay, so those equations basically have to be solved on a computer only. So yes, computer programming, which was not covered in this course, has to be explored. So what I can suggest is you can try writing a computer code for Newton-Raphson method for single variable nonlinear equation and system of nonlinear equation. If you can write a computer code for that, then you'll be able to write a code for nonlinear this finite element equations. So, Mr. Ashish, does that answer your question? Mr. Ashish? Okay, I think I'll move to the next question. So Mr. Harsh wants to know which software shall we use? So I think, Mr. Harsh wants to know, I think, regarding which finite element software. Is it not, Mr. Harsh? If I'm getting it correctly, you want to ask which finite element software you want to use, right? Mr. Harsh? You can type yes and then I'll proceed. Mr. Harsh? Okay, so let me proceed. So I think you mean any finite element software. So one of the most popular software for the currently being used in academics for okay, so let me ask software thing first. So one of the, some of the most commonly used used are Abacus and Console, which people generally use, because in both the software you can carry out, I mean, Console is for multiphysics and mostly for multiphysics people are using, and Abacus is mostly you have a lot of options there. I mean, you can put your own elements, you can put your own material model. I mean, everything, there are subroutines that can be programmed. And also some people use ANSYS, which is more, I mean, I would say more catered towards the need of the industry rather than academics. So that's what I will say. And there are very specific software, like for fracture, there is Frank 3D, Frank 2D, all this software. There are many open source softwares. Okay, so if you cannot get access to these commercial packages, then you can use one of the open source software like Calculix, Phoenix, all these. Okay. So next question is how effective the push forward operation is as we used it for linearization of internal virtual work, week 10. How effective the push forward operation is. I mean, I'm not getting this question, what you mean by this. Let me open the lecture slide for that week. Week 10. Linearization of the internal virtual world. Okay. So in push forward, yeah. So first, I think why we needed this. See, first of all, the internal virtual work expression was written in the current configuration, right? So if you see question 11 of these slides on lectures 25 to 26, so slide number 8, sorry, slide number 10. So if you see equation 11, so the internal virtual work is written in terms of the Cauchy stress tension and the rate of deformation tension over the current volume. Now, since we do not actually know the current volume, which is the unknown, so we have to first of all express that integral in terms of the integral in the reference configuration. Okay. So once we know the reference configuration, then we can take the directional derivative. Okay. And that's what is done in equation 12. So there the directional derivative operator D can be taken inside the integral. And then you can carry out the linearization. And once you have completed the linearization, because your equilibrium has to be satisfied in the current configuration, you can push forward everything to the current configuration. That was the what you get in equation 37. So can you brief some research application where this course will be more effective to be applied? Okay, so I mean, in any, for example, I will give my own example, my research work. So we do research work in adhesion, for example, impact problem. Okay, I mean, you have ductile fracture, you have like biomechanics application. I mean, for example, modeling of beating of heart, wound healing. Okay, all these are I don't work in this area, but I usually work in the development of computational contact algorithm. Okay, so there it is used a lot. The core idea of this course is used a lot. Okay. So I mean, wherever you'll have a material which is undergoing large deformation, okay, large deformation with respect to its constitutive relation. Okay, I mean, large, basically for steel, something is large, and for aluminum and for rubber, that is not large. So large with respect to that response of that material. So wherever you have these kind of responses, you will find application of this course. Okay. So Mr. Ashish, does this answer your question? So every field where you have any material, be it metal or your tissues or you have rubber, whatever, wherever you have some material with some loading, you will find application of this course. Okay. So Mr. Harsh, okay, so okay. Yeah, so in the area of research program in computational mechanics, okay. So what I would suggest is maybe you can drop me an email, okay, and that would actually be a right place to discuss that. I mean, here it's not possible to discuss. Maybe if you know my email ID, you can drop me an email and I'll be able to help you out. IIT Guwahati, for example, has a MTech program in computational mechanics. Okay, so it's a very good program in computational mechanics. We work in that area. And then even outside India, there are places where whole centers are there. For example, Aachen Institute for Computational Engineering Science in Aachen, Germany. So there also you have computational mechanics people working in wide array of domain in multi-physics domain. Okay, so you have a lot of fields. So you can drop me an email and then uh, I'll be able to tell you in more detail. Okay, is it fine, Mr. Harsh? Yeah, Mr. Harsh, is it fine? Yeah, Mr. Athar, any more questions? Mr. Harsh, Mr. Ashish, Mr. Athar, I mean, Mr. Praveen Kumar, uh, do you have any question? Any more question? You still have some time. Yeah, okay. So, Mr. Athar, it is fine if you can email me. I mean, my email ID, I think you know. So you can type my name on Google. It's available on the IIT Guwahati Mechanical Engineering website also. So you can type. I'll be happy to reply whatever queries you have. If I know, I'll be definitely be answering a question. It is okay. It is perfectly fine. Okay. So Mr. Harsh, Mr. Ashish, any more questions? Mr. Praveen Kumar? In case nobody has any questions, can we close? So in case nobody has any question, can we close the session? Mr. Harsh, Mr. Ashish? Okay, so assignment is very tough. Okay. Okay, maybe from next time we'll try to have a little milder assignments. So, Mr. Ashish, if you can specifically say which part, all the assignments in all the weeks, were they tough or only some few weeks? Okay, so in case nobody has any questions, so thank you very much. So we'll like to close this session now. Okay, so if possible and feasible, a project component could help better understand the concept. Okay, so project component, maybe Athar, you can mail me in detail, or we can set up some meeting where you can tell me in detail what kind of project component can be there. Because it's mostly a theoretical, I mean, like very core course. So that would be helpful. So maybe you can tell me in details. Okay. Okay, after 5th week. Okay, so the second half of this course. Okay. So, okay, so maybe thank you, Ashish. Maybe from next year we'll try to see we can make it a little milder. Okay. Okay. So thank you very much. Thank you. Thank you all for joining. And I hope this course was helpful to you. And we tried our best to give you a taste of what basically computational mechanics in general, in particular, nonlinear finite elements are applied. And surely this should be of help if you pursue research. And I wish you all the best. Thank you. Thank you very much.